In this video, we're going to talk a little bit about the regression statistics using Excel and highlighting kind of how they come about. So this is a little bit of a busy spreadsheet, but let me just explain to you kind of what I did. So I started off here with some data. I started off with these data points, and you can see from the graph this data is very, very linear. Okay, so there's clearly a linear relationship from looking at it, and we're going to see that's reflected in the statistics. Okay. From this data, I did my regression. So I went to data, data analysis, did my regression. I put in my Y range, B1 through B20, put in my X range, A1 through A20, selected labels, put an output range and told it to drop it down here in A22. And it's just telling me I've already done this. And so this gives me my regression statistics. And you can see here we've got our R squared value, 0.977, very, very high, close to 1, as we expected. And then if you look below, you've also got these other values that I was talking about. Okay? So you've done this F-test. You've gotten an F-test statistic. So that's right here. The p-value that I was talking about is here under significance F. Okay, so that's the p-value. If that's less than 0.05, then we would say that this is significant at the 95% confidence level, that the linear relationship is significant at the 95% confidence level. And you'll see here it's 1.8 times 10 to the negative 15th. It's very, very small, much smaller than 0.05. And that's because, again, we have a very linear relationship. Okay? You can also see under the down here where we had got our coefficients. So remember, this gives us our intercept, our B, and our M. We have a t-test that we've done, the t-statistic. That's gotten us a p-value. So the one that we're interested in here is the one for the variable year. So that's what that's saying, is that if this is less than alpha over 2, so less than 0.025, which it is, 1.86 times 10 to the negative 15th, exactly the same as for the F-test. If that's less than 0.025, then there's a linear relationship. Okay? So again, the F-test and the t-test give us the same information here, but these are the numbers we want to look at. For the F-test, this needs to be less than 0.05. For the t-test, this value needs to be less than 0.025. Okay? It also gives us our confidence intervals here. So you can see we get a confidence interval for B. So what it's saying is that the most likely value for B is 27.57, but that we're 95% confident it's between 24.72 and 30.41. Similarly, the most likely value for the slope is 3.21, but we're 95% confident it's between 2.97 and 3.46. Okay? And you can see this confidence interval gets repeated twice. That's because you can put another one in if you want to get a different, say you wanted a 99% confidence interval. You could also get that. Okay? So the last thing I have here is what I've done is I've plotted the data on this graph. So you can see the blue points are our data. They kind of go up and down. The orange line is our y-hat projection. So that's using 27.57 plus 3.21 times x. Okay, and you can see that's pretty much down the center of the road. And then I've also graphed the max and the min of that 95% projections. So you can see the gray is kind of the minimum. That's using these lower values, 24.72 and 2.97. And then the upper, or the max, is using the upper values, 30.414 plus 3.47x. And so you can see that, and this is not always the case, but it frequently will be, all of our data values are kind of between that minimum and that maximum. Most of the data values, 95% of the data values, roughly, are going to be between the min and the max, or should be in a normal case, okay? If there actually is a linear relationship. So let's look at what this looks like when there's not a linear relationship, okay? So this data, very, very linear, behaves very well. if we look at this next data set, this data set is nonlinear. I got this completely with random numbers. You can see it's a mess. It's all over the place. There's really no line through it, okay? And so the statistics reflect that. So I did a linear regression on this. I got an R-squared value of 0.04, very, very close to 0, not close to 1. So remember, that means only 4% of the variation is explained by the by a regression line, okay? And so you can see here, when we do our f-test, the significance is 0.36, 0.37 actually, if you round up. And so that 0.37, much larger than 0.05, and so that would tell us that in our hypothesis test, we would choose the null hypothesis, that there is no linear relationship, okay? Similarly, for the p-value for our y-intercept, 0.365, 0.366, the exact same value telling us reject the linear relationship. There's no linear dependence on this variable, okay? And so that's what it's going to look like in a nonlinear case. Now, one thing to be cautious of, if you have data that fits some other kind of model, so like an exponential or a power model, you may find that the significance says, oh, you know, this fits a linear model, because it may be close enough that there is some sort of linear dependence. What we're going to see is that another model gives us a better fit and better significance and all of that, okay? So that's the idea. It's not so much that necessarily this says this is the best model. What it's saying is that with 95% confidence, we're saying this model could fit this data, okay, that it could have come from this model. We're not saying that it necessarily does, and that's kind of an important realization to have, okay? So in the next lecture, we're going to talk about multiple regression and how we can do these statistics with multiple regression.